Thank you, York, for the introduction, and thanks to everyone for coming here for the first talk in the morning. So, I'll be talking about new implementation for the spell utility that I have been working on for about 1 year. So, a bit of an introduction about myself. As York said, I worked about 5 years back for NetBSD in the Google Summer of Code program. And so I worked on writing a new implementation of the apropos utility, which had a full text search feature. And I got the NetBSD commit bit about one year back. And so this project started about at the same time. So I'll be talking about this. So these are the 5 major topics I would like to cover today. So I'll briefly talk about what are the shortcomings in the current spell implementation that is there in the BSDs. So from now onwards, I would like to call this the old spell implementation, and what I have been working on, I'll call that as a new implementation. So based on the shortcomings, I have come up with a set of features or requirements that a modern spell implementation should have. I'll talk about some implementation details that I have done in this project. I'll compare the performance of some of the major spell implementations and with this implementation, and I'll show one small demo of integration with other shell utilities of how to use spell check. So this idea of a new spell checker came to me when I was working on the Google Summer Code project about 5 years back. But at that time, I realized that writing a spell checker is not trivial, and I could not do it in the Summer of Code. And I dropped the idea at that point of time. And about 2 or 3 years back, David Holland created a bug that we should just remove the spell utility from NetBSD because it just doesn't work. So he cited several examples of some invalid spellings, and spell will just never complain that those are incorrect words. So at that point of time, I volunteered that, and I said that I would like to work on this. And I finally got around and started working on this last year. So I'll talk about some of the shortcomings that spell has. So it's a very old implementation. As per Wikipedia, it was created around Unix version 7 from AT&T. So Douglas McElroy created this implementation as spell. He's also credited with creation of, I think, diff, sort, tr, join, and some of those utilities. He also created this spell implementation. So the problem with this implementation is that it uses, to decide whether a word is a correct spelling or not, it uses a set of rules called inflection rules. So essentially, these rules are, so when looking at a word, if it will first check whether this word exists as it is in the dictionary or not. If it doesn't, then it has a list of prefixes and suffixes. So it will remove, if it will check that whether this word consists of any of these prefixes or not. If it does, it will remove all those prefixes. Similarly, it will check for all the suffixes. If it has any suffixes, it will remove those. And finally, whatever is left, it will check whether that word is in the dictionary or not. So as it happens, if you saw that, so these are all popular suffixes. So fragment, fragmental, froghood. If you add any suffix to a word, a spell will think it's a valid word, because if you remove the suffix, whatever remains is also a valid word. So while it's a handy trick to do, but it's quite inaccurate. And another major drawback is that all these rules are strictly applied to the English language. So you probably will not have all these prefixes and suffixes being useful in other languages. So if you want to use the same spell implementation with a different dictionary, it will probably not work unless the language is English or English-like. And another drawback that I consider a missing feature is that it does not give spelling correction. So it just checks whether this is a correct word or not, but it will not say what should be the correct spelling. And finally, it lacks a library interface. So for example, when I was working on Apropos and I wanted to integrate spell checking functionality, but even though there is a spell checker, I could not use it because it doesn't have any library interface that I could just call some APIs and do it. So I would have to end up implementing the whole spell checking interface myself. So based on these shortcomings, I have come up with these set of requirements. So just apart from doing a spell check, it should also do spelling suggestions. So it should come up with some possible correct spellings for the misspelled word. It should also use algorithms which are not strictly tied to the English language. So for example, those inflection rules will not work with other languages. So if we can come up with algorithms which don't use such kind of rules, that will be good. So we can use the same implementation with a different language dictionary and it should work. And it would also be nice to have a library interface. So other applications, for example, the shell or Apropos or similar applications could also easily hook up and do spell checks. So as part of this project, these are the four major things that I have done. So I've created a bigger dictionary because the existing dictionary that is there in NetBSD, that is user shared dict words, it doesn't have all the words, so I worked on expanding it. And then I worked on writing a new spell implementation using some of these algorithms, the edit, distance, double metaphone, and the tries. I compared the performance against some of the other open source spell implementation, such as ASpell, iSpell, and HunSpell. And I also tried to integrate with other, for example, with the shell to see how easy it is to integrate. So the existing dictionary that is there in the BSDs, that is the user shared dict words, it is the Merriam-Webster's dictionary, but the problem is that it does not have all the word forms. So for example, if there is a verb, it will not have its past and other verb forms. Or if there is a noun, it will not have the plural forms. So that's why the old spell implementation used those rules, because it could use those rules, and even though dictionary doesn't have all those possible words, it can remove the prefixes and suffixes and it can still figure out if it is a correct spelling or not. But if you want to get rid of those rules, we need to have the full dictionary with all the possible word forms. So I expanded the dictionary, and so this is the difference that I have currently. So the old dictionary had around 235,000 words, and the size was about 2.5 megabytes. And the expanded dictionary has around 421,000 words, and the size is around 4.5 megabytes. Now, talking about the spell checking issue. So when we want to do spell checking, there are two major kinds of spell checking errors that can be made. So one is non-word errors. So for example, if you misspell applied as apple, so if you miss the I, then it becomes apple. And apple is not a dictionary word, so that is not a real word. So it's a non-word error. We can easily figure this out. And then there are real word errors. For example, if you want to spell desert, but if you add an extra S and becomes again desert, but that's also a word. Or if you want to write there, but you exchange R and E, it becomes 3. That is also a word. If you want to write peace, and you use a different spelling, that is also a word. These are much harder to figure out. So how do we handle real word errors? It's a much harder problem. Because all of these are actual real words, so we can't just look up the dictionary and say this is not a correct spelling. So we can use bigrams or trigrams to figure out based on the surrounding context. Like For example, if the word is I'll be there as soon as possible, but okay, soon is misspelled, but and now there are two possible corrections to that, sun and soon. But based on the pattern, we know that as soon is much more likely to be there as compared to as sun. So based on that, based on these kind of heuristics, we can figure out, okay, this is not a correctly spelled word and we should replace it with this word. But this is much expensive to do because if you want to do this, you have to scan every word, because you cannot just say, you cannot depend on just doing a dictionary lookup. You have to scan every consecutive pair of words in the file and check if this is a likely bigram or not. So this is a much harder problem and it has a performance impact, so I did not work on this during this project. But I have worked on handling the non-word problem, which is a much simpler problem to start with. So these are much simpler to detect. You just scan through all the words in the file and you check the dictionary. If it is not there in the dictionary, it is most probably a spelling error. And if you use an expanded dictionary, we don't need those inflection rules. So how do we represent a dictionary in the memory? So the old spell implementation used a nice trick. So it used to mmap the whole file, whole dictionary into the memory, and it would do a binary search. So it would just, whatever word is there, it will do a binary search and figure out if it is there in the file or not. Although it works, and it doesn't require a lot of memory, but I believe I did not use this. So my first instinct was that if I want to expose this as a library interface, and if an application wants to do a lot of spell checks, then going through a file like that, memory map file, might not be a good thing to do. So I decided to read the whole dictionary into the memory. Although I have not compared the performance of mmap version versus reading the whole dictionary into the memory, but I have tried some of these things. So we need a fast lookup data structure to represent this dictionary into the memory. So we could use a hash table, but it does not guarantee a worst case performance. So if the dictionary is huge, it might have performance impact. So even though normally a hash table guarantees O1 performance, but in the worst case, it might just become linear. But we could use red black tree also, which guarantees order log n performance. But so if you have a huge dictionary and you want to see whether a word is in the dictionary or not, and you have it represented as arbitrary, you have to do string comparison at every node in the tree. You'll end up doing a lot of string comparisons. Tries are a specialized data structure which avoid this problem of doing that many string comparisons. These are like binary search trees, but every node has a single character, and you just traverse the tree based on matching the characters. So you don't end up calling strcmp a lot of times. So I've used these ternary search tries. So these are much like a binary search tree, but instead of having 2 nodes, at every level it has 3 nodes. And every node stores 1 character of the word. And in the next node, if the next character is smaller than this character, we'll go to the left. And if the next character is greater than this character, we go to the right. And if it matches with the current character, we go to the middle node. So that's how we traverse. So and this also has order log n performance. And another cherry on the top is that we can do prefix matches. So for example, if I want to see how many words are there with a certain prefix, I can easily do that with this kind of data structure in login time. So this is an example of a ternary search try in memory. So for example, if I want to insert a word cat, so I'll start with C, and then this is the first word, we'll just go down the middle node. If I want to insert another node, in another word, let's say bug, I'll go, since B is smaller than C, we'll come to the left, and since there is nothing here, we'll go down the middle. If I want to insert cup, so C is already there, U is greater than C, so we'll come down to the right, and then we'll come again to the middle. And this way, you can do, again, a binary search kind of lookup and insert and get the words in login time. So for doing spell correction, so that was about how do we represent the dictionary. So once we have the dictionary, we can look up the dictionary and we can figure out if it is a correctly spelled word or not. But now to do spell correction, there are different set of algorithms. So one of the popular techniques is the edit distance technique. So we figure out how many edit distances this word is from another word. And then there are sound-based algorithms such as the Metaphone. And we use n-gram models to figure out which is the most correct spelling of all these possible corrections. So the edit distance is basically if we have two words, so how many edits are needed in this word to convert it into the other word. So the possible edits are there. The insertion, so you can insert any character in the word, or you can delete any character in the word, or you can replace characters with another character. And it has been found that a majority of spelling correction are just one edit distance away from the correct spelling.
You don't use transposition?
Yeah, transposition is also there. This is an example of, for example, if the word is, I misspelled da as ta, so then these are the possible, this is not a complete list, I just shortened it, but so for example, if you delete one character at a time, so if you remove the T, it will become EH, and if you remove the E, then it becomes TH. Remove the E, then H becomes T, and so on. So these are the possible words from ta at one edit distance. Once we have this list, again we can look up all these and see how many of these are there in the dictionary, and then those are the possible corrections of a misspelled word. So these are all edit distance 1. If we want to go to edit distance 2, we take all these words, and from these words we go to the next level. How many words are there at edit distance 1 from here? And those are edit distance 2. But as we go on, the list of words increases very rapidly. So looking up dictionary becomes quite expensive. Another popular technique is the Metaphone algorithm. So this is a phonetic algorithm. There was a very popular algorithm called SoundX, which was developed in the 50s or the 60s. And so essentially, based on how a word is pronounced or how a word sounds, it generates a code. So every word gets a code. And based on the misspelled word, we can generate its metaphone, and we can see how many words are there which have the same metaphone as similar to this. And then those are the possible corrections for this particular word. So the advantage of SoundX over, advantage of Metaphone over SoundX is that it covers not only English but also many other languages. So if we want to use it for other languages, this works quite well. And there have been 3 Metaphone algorithms. The first one was developed in 1990, but it had some bugs. And then the next version, called Double Metaphone, came in 2000. And the final version came in around, I'm not sure, but that is a commercial version, so we cannot use it. But the Double Metaphone algorithm is available as open, so we can easily use it. And finally, once we have these possible corrections for a misspelled word, we have to figure out of all these possible corrections, which are the most possible ones. So as I described previously, we can use bigrams or trigrams to see the surrounding words and see how many of these are, how many of these are the most possible corrections here. So this is an example. If I have a sentence like this, I'm not feeling very well, and I misspelled very as W-E-R-Y. Now I'll have I will have corrections such as very, W-E-A-R-Y. That is also a valid word, and I'll have correction as very, V-E-R-Y. Both are possible corrections. But if I compare bigrams, then V-E-R-Y very well is much more likely than W-E-R-Y very well. So this is a technique to filter down this list of possible corrections. And once we have all these algorithms, we have to figure out how to combine all of these to get the best possible accuracy. There are various choices here. So you can just take all the words at edit distance 1 and just stop there. So if a match is found at edit distance 1, just take that. But although that gets good accuracy around 70 to 80%, but it does not cover all possible spelling errors. Another possibility is once you go another distance, so you go to edit distance 2. But edit distance 2 gets, because the number of words at edit distance 2 is much higher, the number of comparisons you have to see in the dictionary is much higher also, so it becomes slower. So what I have found is that these 3 steps. So first, check all the words at edit distance 1. If a match is found, stop there. If there is no match found, we'll try to find all the words having the same metaphone or a metaphone at distance 1 or 2. And out of those, we'll see if a match is found in the dictionary or not. If no match is found, then we'll go to edit distance 2. So this is an increasing order of runtime complexity, because this is very fast. This is also fast, but this is very slow. So with this, we only want to do in the worst case, then when we are not able to find anything. And then in the research literature, there have been some tricks which have been found. So it has been found that there is a much less chance that someone will misspell the first character of a word. So when we are generating the possible correct spellings, if the first word is being changed, then we'll give it a lower weight, because it is very much less likely that this is a person will make this kind of a mistake. And similarly, when we have a set of corrections, and out of those, the words which sound similar, that is, they have a similar metaphone code, we can give those words a higher weight, because they are sounding similar, most probably that could be the correct spelling. So based on these heuristics, I have done some comparison with the other major open source spell implementations. So there is an openly available data set which ASpell uses to publish its benchmarks. So I have used the same data set and compare the performances. So the ASpell, so there are 2 variations in ASpell. There is a normal mode and there is a slow mode. So in the slow mode, and then there is, so this is like if a match is found in the first place, that is, if ASpell is generating just 1 suggestion, that is the correct match. And if ASpell is generating 5 corrections and a match is found in any of them, this is 1 to 10, that is, a match is found in any of the top 10 corrections, and this is the same as for the top 25. So for the first position, ASpell gets around 73 or 74% accuracy, but if we go to top 5, ASpell gets much better, so it jumps to 96.1. And in the top 10, it goes to 97 and then 98. The slow version is slightly better. It has 74 and then 96.6. unspell is better in if we are doing comparing the first match in the first position, so then it will have around 80.5 accuracy, and the top 25 goes to 97. iSpell is the oldest of all these so it has accuracy around 77%, and in the top 25 it goes to 85. So I also have done 2 variations of comparison. So there is a slower mode and there is a fast mode. So in the slow mode, it gets around 91% accuracy, and then in the top 5, it goes to 95, and then the improvement is very marginal. So it almost stops at 95. In the fast version, it starts at 88.7 and goes to 93 and 93.4. So the difference between the fast and the slow mode is that this test data set contains about 4,000 words, and the slow mode takes around 2 minutes to come up with spelling corrections for all those 4,000 words. The fast mode takes around 8 to 10 seconds to do spell corrections for 4,000 words. So I've also created a small demo to show how this works if you want to integrate in a shell. So I wanted to integrate this into an actual shell, but I didn't have the time, so I just created a shell myself and integrated it, the spell checking functionality there. So for example, if I type anything wrong, it will figure out, okay, I spelled the command wrong. I mean, this is an existing functionality that most of the shells already have, but I just wanted to show how simple it is to do this. Then since I'm using a trig data structure and it can do prefix searches, so it is very simple to do auto completions as well. So for example, if I want to see, this is also an existing functionality, but since we already have all the words in the memory, and we can do this kind of stuff also. So, and another thing is, if you want to do context-sensitive auto-completion. So for example, if I want to look up a man page, and I type man, and then I do tab, and then it will auto-complete it to the possible man page name. Yeah, and similarly, if another example of context-sensitive auto-completion is it visible? Okay. So another example of context-sensitive auto-completion is, for example, if I want to install a package and I type package add, and then I want to install some Go package. So I just type Go, and it will show me all the packages that are there for Go. So I built individual dictionaries for man pages, package names, commands, and I'm based on the context. That is, if I have typed man, I'm looking up the dictionary of man pages. If I am trying to install package, then I'm looking up the dictionary of packages. I'm doing auto-completion based on that. So all of this is quite simple to do with a library-like interface. So I would like to conclude with saying that although it does not beat ASpell or Unspell in their top 25 corrections, but it still is able to match in the first or top 5 comparisons. And there is still much room for improving the accuracy and the performance. So because I'm using an in-memory dictionary, there is an issue about using too much memory. So if, for example, if the dictionary is too big, it will consume a lot of memory. So that is something to look into. But it would be nice to have a BSD licensed spell checker plus a library so that we can use in our own applications. And all this code is currently available on GitHub. So it is not part of NetBSD as of now, and I'm not sure if it will be, but I'll try to post it on the mailing list. I'm still working on this, so there might be a lot of bugs still. Any questions if you have?
So are you looking at what keyboard type people are using so you can say what characters are possibly the replacement for a typo?
Not yet. So that is I guess that is a different set of algorithm probably I will have to see because, for example, the edit distance one, so I'm using the normal ASCII order, but if I want to use the keyboard order, then that's a different kind of, I need to figure out how to get that ordering of, how the keys are placed on the keyboard. Yeah. That is a possibility, yes.
So in your demo, you showed your special shell, which was expanding context-wise.
Yes, yeah.
That's one approach. The other approach would be to maybe modify package info manual to use your infrastructure.
Yeah.
What would you propose? Because both of them are kind of intrusive, and somehow there has to be a model which you would use for your deployment of this spelling edition.
So, for example, you're saying, for example, if I want to modify package add, and that should do the auto-completion, or?
Well, the question is, would you build it into the shell, or would you build it into each and every command?
It is simpler to do in the shell because that is one place, and we can modularize it. So we can provide hooks into the shell. The shell should use this dictionary to look up when someone is typing this command. Modifying each and every command will be much more time-taking.
I can answer that because I've written this thing before for TC show. So there are certain common completions. So depending position, if you're a command or you're a file, or if you're expecting a directory or not a directory. So all of these are common. So you can put it in the language of the shell. Putting it into each command would require executing the command every time you have to ask it what the completions are, and that can be inefficient.
One example where I would like to modify the command is, for example, in apropos. So if someone types a query and that does not get any results, but apropos can see, oh, you misspelled this thing as something else. So it can say, did you mean this? So someone can know, okay, I misspelled this thing, I need to do another query. That is one place I can modify the command itself. For auto-completion, it makes sense to modify the shell.
Other questions?
Okay.
In that case, I want to thank you very much for your talk. And we have something for you from Paris.